we are looking at the simulation of Magma Chamber Simulator, how it functions on a Mac platform. But on PC, the functions are very similar. So this is not so different from Mac. There are some small differences that we can return to them later. I think first thing that I'm going to show for you is the input that goes into MCS. So input is recorded in Excel files, surprise. But I mean, that's convenient in a way that you usually have your data for the magmas and the wall rocks in Excel files. So you can directly use that and copy it there. Let's take a look at one input. You can see the list of input files that I have here. I've run a couple of models
a couple.
in the past. This one, I don't know, this is quite small, but we can zoom in later if it's desirable, especially when we are looking at the Excel file. But this one is one from the manuscripts. So the two manuscripts that we published in contributions last November. This is one of those runs, and this is a fractional crystallization run of a basaltic rock, or basaltic magma, sorry, that assimilates average continental crust. And in that simulation also has two recharge events. So there are two cases where we have more magma coming into the chamber. So I will open this. I think I will zoom into this a little bit. Okay, maybe that's good. I guess you see the numbers. Okay.
Yeah.
Okay. So first thing probably to show from here is that before we go into the other parameters is that this is the magma composition. So we have a magma, and this input list of oxides is the same than in melts. So we also have water and CO2 available and can be input. So MCS also treats fluids and fluid separation. And you can see this is a basalt, so it has about 8 to 8% of MgO. And you don't have to input all oxides. I mean, it's not necessary for this to function. So you can see, for example, in melts there is nickel oxide and cobalt oxide. I've never seen a run that actually uses cobalt oxide. So it's such a minor component in magmas that it doesn't do anything basically there. So you don't need input for all of those. Okay, for that you put some kind of starting temperature. I usually put a very high temperature. It can be, for example, 1600. It doesn't mean that it starts from there. It always tries to find the liquidus. So in the first step, it drops to liquidus. So when something starts crystallizing, that's when the modeling starts. So I think it's usually easiest just to put a very high temperature there so that it automatically drops to the liquidus. Temperature decrement is the amount of temperature that drops per step of modeling. So everything happening, let's say that this would start from 1400 degrees, although it probably doesn't because it's quite a high temperature. But anyway, the first step, so temperature drops to 1395 degrees. That step is an equilibrium crystallization step. So at that point, everything crystallizes in equilibrium. And after that step has been completed, all the formed phases are fractionated away from the magma. So basically by varying this value, you can control what is the degree of fractional crystallization versus equilibrium crystallization. So the larger that step is, more equilibrium crystallization there is in the system. So you can kind of like play with that. 5 is usually the number that I've used. If you go to very small numbers like 2 or 1, then it's very like small steps and it takes ages and it's not really giving any useful information. And then you can decide, okay, at this temperature or this mass of melt, the model ends. The mass of the melt, the initial melt, is always 100 units, whatever those units are. Then we have the wall rock composition here. And this is just an average crust, I think, average crustal composition. And here are some input parameters which make more sense when I run the modeling software. So these are used, the first three ones here are used to study the melting behavior of the wall rock. So in melts, when we are modeling with melts always wants to have melt in order for it to be able to define phase equilibria. So it's not a subsolidus modeling software. And for that reason, when we want to model partial melting of wall rock, we first have to consider that wall rock. We have to approach the solidus of the wall rock from high temperature, so that part of the system is molten, and not from below liquidus, below solidus, where everything is solid. So these numbers are used for that, and these will make more sense when I run the program. I won't explain them more here. But that's the way we approach the melting of the wall rock in MCS. The initial mass of the wall rock here is 200 units. So that's twice the amount of magma that is in the model, because magma is always 100 units in the beginning. So this means that there's this amount of wall rock will take part in the reactions, and this amount of wall rock is heated during the simulation. Then we can also decide the initial temperature of the wall rock. Here, the initial temperature is very high already, 700 degrees. But of course, you could start from, let's say, 200 or 300 degrees. That would be like a few kilometers in the crust. But here we have kind of like preheated the wall rock so that the assimilation starts very early. It may be like it could have been preheated by earlier magma pulses or something like that. So all of these values you can change and you can play with them. Then is the input for the recharge events. So there are recharge magmas coming in. I'm not sure if you are going to, Cecilia, need these recharge magmas in your modeling. Maybe, maybe not, if the main point is the assimilation. But anyway, there's an option to put recharge magmas into the chamber whenever you like. So here you define the measurement composition of the magma. I think this one is the same composition than the initial melt. So we are putting another batch of initial melt to the chamber. And you can decide its mass. So this is also a very large number. It's almost at the same size than the initial magma. And you can decide its temperature. You can decide at what point it comes into the system. So all these kind of things you can input. And this is basically, you can input up to 30 recharge events if you like in the system. So this is the input. In the beginning, we have some global parameters which are quite important. First one is how much the wall rock has to be molten before assimilation begins. There is 0.1 number here, which means that the wall rock has to be 10% molten before any assimilation takes place. And that's kind of like we are trying to simulate nature a little bit, because not instantly when a small drop of melt forms in a wall rock, it's not that everything is instantly, assimilated. So we have to have 10% of melt in the wall rock before the percolation threshold is surpassed and the assimilation actually begins. And you can change that number. You can exclude phases from the melts algorithm if you like, not usually recommended because you're altering the algorithm then. You can decide the pressure. MCS is only an isobaric model, so it happens at constant pressure. Maybe I hope that in the future we can have polybaric models as well. One way to do it is that you can have a model at certain pressure, then end it, and then take the final composition from that one and then continue it in the different pressure. So you can have, that's how I've done polybaric modeling with MCS in the past. So I do it kind of like in 2 or 3 stages using different pressure. That's one, not something to really consider about. Oxygen fugacity can be forced here. How I usually done it and how I recommend for Cecilia to do it as well is to use none here. So you are not forcing any oxygen fugacity in the beginning. But as you see, I've already calculated the oxidation state of iron oxide for the initial melt. So after this, phase equilibria will decide the oxidation state. So which minerals crystallizes decides that how, for example, FeO and Fe2O3 will behave. So I give an initial oxidation state for it, but after that, everything is decided by phase equilibrium. By, for example, inputting FMQ here, you could force it to stay open for oxygen. So everything would always be at FMQ. But I think it's more realistic and more natural in a way that the oxidation state changes during the run. Okay, so this is the input. That was quite a lot of talking. When I show the modeling, we can look at what it actually does. Do you have any questions related to this input sheet?
Quick question, if you don't mind, Jussi.
Yeah.
The wall rock melting, you said it starts at 10%. I mean, it's important and quite realistic, as you say, that wall rock is not just 100% melt, and you also need to have a certain amount of melt present before you can really get it out. So are you flexible on this value? Could it be 5% or could you set it to 50%? What's the consequences if you play with that?
Sure, you can input any value here that you like. So,
okay.
So this is kind of like a standard 10% is kind of like a standard for, let's say, crustal rocks. It could be even more. But you can, for example, let's say that you have a very hydrous basaltic wall rock, for example, like maybe in Katla. You could put that lower because if there's very hydrous melt forming and the rock is hydrous, that will probably you don't need that much melting for the assimilation to take place. What is different between that number, how it affects the model, is that if you have, let's say, if you would put like 0.5 here, which would mean that the half of the wall rock should be molten before assimilation begins.
I see. Okay.
You need to heat the wall rock quite a lot before, I mean, it's that amount melted. So the assimilation is delayed. And also another consequence is that melt batch then, that huge melt batch that will get assimilated, or I mean, it's only the part that goes above 50%. So everything above 50% will get assimilated. They are not that enriched in incompatible trace elements.
That's example. My next question.
Yeah,
are you actually does the software account for initial small percentage melts being particularly enriched in some of the incompatibles? Super, excellent. Thank you very much.
Exactly. So it has an effect on that value.
Yes, that would be the consequence indeed.
Yeah.
Wonderful that the software is able to handle that. Great.
I also have a question. Francis, go ahead.
No, it's fine. You go on.
So when I think it's the orange panel below, when you say the amount of rock you're putting in, I remember you used that 200. You see, like
yeah.
I mean, but I see there's grams there, but I guess it's units, right? I mean, so
yeah, it's any units. That's yeah.
So 200 would mean twice the amount of the initial magma. But
yes.
I mean, what is that number telling me? That the model thinks about like virtually 200% assimilation of my wall rock. Isn't that unreasonable? Isn't that too much? Or
no, that doesn't mean 200 grams of assimilation. It means that there's 200 grams wall rock that is playing in this open system. It may be that it won't get assimilated at all. It's then decided by thermodynamics. So that's just the amount of wall rock that is included in the simulation.
Okay, so what is, I don't know, but what's a reasonable number? Do you think 200 is like a standard number I would use there? Or for some reason, I don't know, you played around with that number, putting it very much lower or much bigger? What's the meaning of it?
This is a very good question, and this is something that is important to understand here. I think that is related to this very good question, that in how MCS functions currently is that it doesn't consider thermal gradient in the wall rock. Mm-hmm. So all the heat that is received from latent heat of crystallization of the melt is transported to that whole mass of the wall rock, and that is very high in this simulation because we wanted to show this kind of example in the manuscript. So I would personally, what I've used for my modeling in the past has been 100. So there's equal amounts of melt and equal amounts of wall rock. That's how I would start with that. Maybe if you want to, experiment using different masses and see how it changes the system, that you can do it. But I would usually recommend 1-to-1 ratio of magma and wall rock.
Okay.
Okay.
Can I ask a quick question? Maybe
Yeah, sure.
maybe I'm jumping the gun, Jussi. Maybe you're going to talk about this later, but this is a modeling approach based on major elements. Is there a trace element or an isotope model in the Magma Chamber Simulator?
Yeah, there is. You can model 48 trace elements and 8 different isotopic systems, but it's only something that you do after you have done major elements. So I will return to that later.
Yeah.
So you were kind of like ahead.
So
in that. But I mean, it
something
was a perfect question at this stage because I can
Great.
I mean, explain it. The reason that we are doing that later is that in order for you to model the trace elements, you have to know the phase equilibria. So which phases are stable, because then you can decide the partition coefficients and so forth.
Okay.
When we have the input sheet here at this stage, we don't yet know that what are the stable phases. So that's kind of like we first run the major models and the phase equilibria, and then after that, after we know how the system functions, then we can run the traces.
Great. This is really comprehensive then. It's all building on in steps.
It's basically melts plus the EC-AFC. That's.
Sorry?
It's basically melts, marries, EC-AFC.
Yes, that's true. Exactly how I understand it.
That's
indeed.
Exactly how it works.
This is where I hope that Carolina can really kind of push the envelope on these kind of data that we have and that she's collecting, so that we really get a new picture of all this. So the next generation of modeling, I think.
Yeah.
I hope so, at least.
Yes. Something what I would like to say to Cecilia is that, you know, I've been designing this program and using it for 3 years. Everything here is very natural to me, and all the time I see any row, I instantly know what it means. So I think for many people, I've seen this before, that for the students, for example, you show these huge Excel sheets and this complicated thing, and it feels like, okay, this is too much. I mean, I can't handle it, but I'm willing to help at any point if you have any questions. And it's just, you know, one thing that you can do is that you can't break this. It's also a good thing in modeling that you know you can go to a lab and break an instrument, but it's very hard to break MCS.
Yeah.
So
you can always start a new model. Yes.
Yeah, you can always start a new model, and you can just experiment and try if I put this number here. I mean, I don't understand what it means, and then you read, okay, this is what it actually means when you see the output. So I mean, it may feel like a lot now. I'm sure it feels, but once you run, let's say, like 5 to 10 models, it takes some time for you the first time to run them. But at some point, you are just, you know, okay, I know how this functions now, and I can use it for whatever purpose there is.
No, and it's great because we don't have to go to any labs. We can do this, or Carolina can do this on the PC. Even if it takes longer, I don't know how long the calculations take, but you can use the office PC, Carolina. You don't have to block your own machine with it. So it's actually quite great. It's a perfect Corona thing to do, I think.
Yeah, like I explained to Val previously, that I was well, it's been very different, the effects of Corona, but for me, having this modeling software here at home has been, I mean, it's worked very well. But I mean, it's different for people who were supposed to go to labs. Like I guess Cecilia was supposed to go to do some isotopic work.
Yeah, Carolina was supposed to go to.
Oh, am I missing? Have I mentioned the wrong name? Or I'm sorry.
I think so, but no. I think
sorry,
it's okay. It starts with C as well. So.
Yeah. Yeah, because Caroline wasn't it? She wasn't high enough in my Zoom. So
I see. Yeah.
I got the name. I didn't see it. Sorry, Caroline. This was not in person.
So no, we had all sorts of kind of plans at the beginning, but well, things are more complicated. And now, I mean, the isotopes are done remotely. The stable isotopes. Oh well, you worked with Chris Harris in South Africa.
Yeah.
So and he's doing the stable isotopes now, but. So yeah, and then there is some textual work we are hoping to do, but at the moment everything is locked down. So modeling is actually great, and that means we don't have to emphasize so much the other aspects. I mean, if the modeling turns out well, that's going to be a major thrust of the thesis, and that's great. And given the kind of descriptions that you offer, i.e. the combined melts and AFC, energy constrained AFC aspects, with using all the isotopes, the existing ones as well as the new ones, That's going to be great. I actually think he's going to be better than before for this particular part.
Yeah, I hope so. I think when you described the thesis subject in our previous call, I think that made sense in terms of MCS. Like already snap. Okay, this is, you can do, at least try it with this and see what comes
Absolutely.
out.
No, it's a very good match, I think. And yeah, then of course Harri has some work he's doing right now, and Fran just gave him comments a few hours ago saying, I think you need to do some modeling. So here we are.
Yeah. And melts is very well calibrated for basaltic compositions. So and some that are not very hydrous. So although the wall rocks may be hydrous, but if the melt itself is quite dry, it usually works very well for these compositions. So also the environment is something that fits in the scope. So that's good news for Caroline.
Yes, I think so. Yes, I know it's not perfectly well calibrated for the more felsic or alkaline compositions, but I mean, you can always try what you get. There's no harm in doing that. And I mean, as long as you're honest and you're saying this is what this model gives you,
that's right.
Then that's fine. You don't have to say this is, you know, the ultimate truth. You just have to say this is what this calculation results in.
Yeah.
And if you do a problem audit at the beginning, if you just be honest about it, then there is no issue, and this is publishable. So this is a great tool to work with existing data and squeeze, as I would say, squeeze the last juice out of the lemon from these data that are out there in the literature. And so, yeah, no, this is good. And yeah, I sympathize with what you say. At the beginning, every kind of modeling is a bit overwhelming, but this is why I stressed at the beginning that this is a warm-up meeting as far as I see it, so that Caroline and you have a chance to meet, and that Caroline gets a first impression, and we'll take it step by step afterwards. And it's very kind of you, Jussi, to offer that there could be more meetings where you can help, and we'll get there. So I'm very confident.
Yeah. Okay, let's start the thing.
Okay.
Some enables and OKs in the beginning. Okay, this is how the interface looks like. I think I will zoom into this as well. Yeah, maybe that's better. So here are all the functions that you can do. You rarely need more than, let's say, 4 of them. And I will just show now the input that I showed you. There's magma and assimilating quite a large, or heating and assimilating potentially quite a large amount of wall rock, and 2 recharge events. That's the run that I'm of course trying to run with this. So what we are going to first do is that, like I mentioned in the beginning, we have melts running in the magma, we have melts running in the wall rock, and we have melts running in the recharge magmas. So we start those melts engines for the run, and for that we open the terminal window, and in PC, on PC, this is the command prompt. So it's just a different name, but the same function. So let's start it, or let's start the engine. So here you will get a new window that tells you which melts version you want to use, because there are different versions of melts. I don't know if you see them, but probably we don't have to take too much time explaining these different versions now. But for basaltic systems with basaltic magma, usually what is recommended by Ghiorso et al. Is 1.2.0, and that's also the most recent version, and that also includes the fluid species. So I think that was already chosen as a default. So then we will start the engines in this terminal window. So first the magma engine, then the wall rock engine, and then the recharge engine. So they are now these I don't know how you call them, these meters here going crazy, tell you that, okay, magma melts is ready to run, wall rock melts is ready to run, and recharge melts is ready to run. So it's kind of like it has started the melts engines for the modeling. So then we select the input file, and we can give a name for it, like for the output, like best model ever, or something. This is just a testing name. And then we select the correct input, which I guess was the MES R2AFC input. Yes, that was the one. It actually takes a little bit more time now when the Zoom is running. It's usually a little bit faster. Okay, so now it's this. We have started the engines. It has decided, or we have given it the input file, so it knows what it's going to model or how it's going to start with. Now we treat the wall rock in the simulation. So it now approaches the wall rock solidus from high temperature downwards and tries to find where the solidus is, because we need that information if we want to heat wall rock from below solidus, because melts cannot model, like I said, cannot model subsolidus temperatures and phase equilibrium. So that's why we have to approach it from this direction in order for us to know when the melting begins in the wall rock. And that's where the input values were used, or how the input values for the wall rock were decided in the input file. That may sometimes require some testing that you run with different testing values, so you learn how the wall rock behaves. So this is a little bit complicated part of this, but again, like I said, you do a couple of runs, you get an idea that, okay, this wall rock behaves like that. You can then test or use the same values at least to begin with. If you are using same wall rock in all your runs, you can only do that once for one model, and then in the next models you can just impose the last solution. So you don't have to run it always again. And that kind of like makes your modeling faster if you are using the same wall rock in all your models. Okay, so let's see what it does. Now there's a graph coming in. It's not visible. But yeah, you can read the temperature and the amount of liquid in the wall rock. And you can see that it proceeds downward. So when temperature drops, there's less and less liquid in the wall rock. So of course we are going towards solidus here. That's what we want to define in the model. And you can also read that how much of the wall rock is molten. So at about 780 degrees, we have about 30% of the wall rock molten. It's now going towards solidus, trying to model its behavior in this temperature regime. And at the given pressure. So we have 2 kilobar pressure in this model. Now it's almost solid. And I think this will reach the 0. Yeah, now it's solid. So it found the solidus for the wall rock. And it should report as okay, we found the solidus for the wall rock. And it says that at 740 degrees Celsius, is the point where it's about 10% molten, which was the 0.1 that we gave for the how much the wall rock should be molten before assimilation begins. So it tells us that will happen at 740 degrees. So assimilation will begin when the wall rock has been heated to that temperature. Okay, so that's it. Now we can just start the model, like the full scale thing. Run MCS. For some reason, this is I feel that like this is functioning a little bit more slower than usual. It may have something to do with the Zoom sharing. But let's see. Usually simulations take about from 5 to 10 minutes, but not usually longer than that. We would still like them to be faster, but because there are these different melt engines running and then the Visual Basic is communicating with them, that's where all the time is spent.
That's nothing, Jussi. I remember the days when I did my PhD and there was running melts on some computer in the other hall because we had to go there because there was only one computer that could do it. Oh my God, it took ages, you know. So no,
Yeah.
this is great. 10 minutes sounds amazing.
This is always a matter of perspective, of course. So.
Absolutely. For old gentlemen like myself, this is fast. So.
Yeah, I remember actually my professor who taught me mineralogy when I was studying my basic studies. He explained to me, he was an old person already at that time, and he explained to me that when he was a student, they used to calculate the CIPW norms for rocks, and they did it by hand, and it took 3 days to calculate a norm for one rock. And now we have an like Excel table with 10 kilobytes.
Think about the refined structure of a mineral.
Yeah, exactly. So yeah, it's always relative.
CIPW norms by hand, actually, or on paper when I was a student. Oh my God, it was such a painful exercise. I mean, it gave me a good feeling for it. I still feel very connected.
Oh yeah. Yeah, you accomplished finally. Until you find out that you made a small error in the first calculation. Okay. So there's, as you can see, you can follow this in different diagrams. I'm zooming in Excel now, so you would see a whole variety of different major element diagrams. But you can see that this is where we started from. This is, I guess you see MgO is there, and this is SCO2 on the y-axis. So there's crystallization first, and I guess this is the point where the wall rock has been heated enough that the assimilation begins. And you can see there's an instant jump in SCO2 when the SCO2 rich from the partially molten crustal rock will, you know, start being fed in the magma. And then we have this weird thing going that it's actually going backwards towards the initial melt composition, and that is where the first recharge event occurs. So we have the recharge event pulling it back to the origin because the composition of the recharge melt is the same than the initial melt. And I guess there's another one coming in quite soon. So you can already see here that you can get quite, let's say, unconventional modeling trends here using this input. So it's not like you have a straight line or just a logarithmic curve like in AFC, but it's, you know, with controlling these recharges and assimilation where it kind of, you can have really complicated patterns that you can actually get from a single simulation like this. Something that you can't actually affect here is to actually during run change the axis of the simulation. So sometimes when Excel decides, it sometimes zooms out and zooms into the simulation. So sometimes it's not so easy to follow what is going on. But anyway, all the information will be stored in the output. So this simulation will run until, like usually MCS simulations are running when there's AFC taking place, assimilation, there's wall rock and magma, until magma and wall rock reach equilibrium. So they both reach the same temperature, because then the system is in equilibrium. And that's kind of like where the simulation ends, because it has found equilibrium for the system. So you can read here that magma now is about 1000 degrees, and there's about 66 weight% of liquid in the magma chamber. The wall rock temperature is about 860, and it's about 15 weight% molten. So everything above 10% is going into the magma.
It's quite amazing to see somebody doing work on my screen without me having to do anything. Thank you, Jussi.
maybe we can stay like this, you know, each of us like one at a time shares his or her screen and everybody else can just look at what he's or she is doing. Yeah, I mean, I'm not doing anything now either. I mean,
that's true, actually.
It's that guy there who is doing everything.
Yeah, the software. You are right.
And I think it's finished now. No. Stuck on the last step. Okay, now it's there. So wall rock temperature is about the same than the magma temperature. It doesn't need to go any steps anymore. Everything is fine, okay. Only thing left to do is to export the results. There are these other buttons if you want to do only fractional crystallization or recharge fractional crystallization, then you don't have to care about the wall rock things so much. So then you can just proceed and run straight without consideration of the wall rock if you want to do a simpler model. So these are, for example, those options are available. And you can click them here. So these are only buttons that you need for a standard fractional crystallization model. Okay, but let's export the results here. Something that I probably should say at this point, the run that I'm running here is something that I've run before, and it's one of our example cases.
Okay.
It's very likely that anyone using MCS for a little bit longer will find a model that will crash. Like melts will not find an answer. Okay. So sometimes in melts is not a thing that will find a solution for all possible compositions. So there may be an input parameter or certain condition that melts just can't, you know, reach a viable condition, a solution for that. And MCS will tell you that. It will tell you that, okay, melts crashed, like this model doesn't work. Then usually what you do, what I have done, is that you change some input parameter a little bit, something that probably doesn't matter that much. Like, for example, the wall rock mass, if it was 100, you can try with 105 and see if it's different, because sometimes it'd be a very small thing that the melts ends up in a space that it doesn't find solution for. So
also in the initial, I usually found the running melts. If I put 0 water in the initial composition, that would not. It doesn't like it.
Yeah, it may be.
You can even put 0.2 or something like very, very small, but yeah, it helps a lot.
Yeah, it's a very good advice, for example, to change the water composition a little bit. Yeah.
Yeah, I can see that water makes a huge difference for melts, because obviously the melting behavior will be fundamentally different. And a bone dry composition is really hard to kind of melt. I mean, so I can see that melts would find it a bit exhausting if it was really kind of absolutely dry. So
I can also say that to Caroline that if you get, you know, some of your first models crash, don't be afraid of that either. You will find some that function. I'm sure about that.
It's not some lab gear, so you don't have to. You're not.
No, yeah. Okay, so we can close it and never save on this. So always click don't save. Excel is obsessed with saving. Okay, then we should have the output here. Somewhere. What was the name? Oh, it was something best model, something very silly name. Oh, here it is. And this is also a place to get overwhelmed by the amount of input or output in this thing, but we don't have to go through it all here, because most of these, I mean, it would take an hour if we go through all of this. But basically the columns are quite self-explanatory here. It tells you when there's fractional crystallization step, when there's assimilation step, when there's recharge event, and they have also been colored differently here. You can follow the temperature of the magma drop and the temperature of the wall rock rise. You can follow the masses of the liquid and the magma chamber. You can follow the masses of the crystallizing phases, the incremental phases, and the bulk cumulate as well. fluid information about the recharge magmas, information about the wall rock and how much assimilation takes place each step. You can see here, for example, if we pick one random number here, it says that the first assimilation step, we assimilate about 4 mass units of the wall rock melt. And you can follow that it actually rises a little bit later. There's some phase that melts more than in the beginning, so we get more melt input into the magma chamber in the beginning. And of course, it also records the cumulative amount of assimilation. So what is the total amount of assimilation? And all of these, like I said, endless values here. Then it gives you the phases that crystallize in the magma. So this much olivine is the first phase to crystallize, gives the incremental amount of it and then the cumulative amount of it. Next one is Clinopyroxene. First step where Clinopyroxene crystallizes, it crystallizes 2 mass units, so quite a lot compared to olivine in this case, and so forth and so forth. You can read the wall rock mass constraints, which phases are present in the wall rock. You can see there's biotite in the beginning, but it melts like during the first steps, it's already gone. So you can see that biotite is the first phase. It's the water-bearing phase. That's the first one being destroyed.
It should be gone immediately. So.
Yeah, it should be gone, and it is gone. And after that, I guess we are losing, most of what we are losing from the wall rock is quartz and feldspar. So kind of like following the common Bowen reaction series in a way, but of course thermodynamically constrained. Mm-hmm. And the wall rock will get more mafic as the system proceeds. So then something that will be probably most important for Caroline also and for most modelers is the major element composition of the melt. So you can basically just copy it from here and plot it to whichever plotting software you are using. So you can follow it here. Like we suspected, you can see that the SCO2 content is pretty same during the first steps when there's crystallization, but when assimilation begins, SCO2 contents go high because we have SCO2 rich melt coming from the wall rock. And then first recharge of primitive magma, again taking it back down. Same for the recharge, and you can also read the wall rock melt composition here. So what is the composition of the wall rock melt in the beginning or during the run? And this is not the only tab. The input is recorded here as well. So every time you do a model, you store the input in the same file. So you never lose that, okay, which model was this one, because the input is stored there.
Very useful.
Yeah, it is very useful because when you have, let's say, dozens of these models and you would not have this information, you would be completely lost.
Yeah.
Then some diagrams like dust diagram and different mass fractions of the different phases. I guess we don't have to look at these in detail, but you can follow how the masses of the phases change during the run. Something that may be important also for Caroline is solid formula. So this is very small, but maybe. So you can read the compositions of the phases each step. So let's say in your Katla system, you have a feldspar or pyroxene or something that has a certain composition. You can follow in this model also the composition of the minerals, like one is the anorthite content of the plagioclase, what is the forsterite content of the, actually this is the wall rock, so let's go where the magma comes in. Here's the first magma. So what is the composition of the first olivine? It's 82 forsterite content. And you can read the magnesium number of Clinopyroxene and so forth from this table. So if you have mineral compositional data, you can also compare it to this output. Okay, so huge amount of, again, you can easily get overwhelmed by all this output that it takes. I've learned that with the students who I worked with and other collaborators, one of the main cruxes in using MCS is to find the information that is relevant for your system from this huge amount of output. And again, if you feel lost with that, like you don't know what to concentrate on or whether you're anything you think makes sense, you can just again contact me and ask if there's something that like if I could maybe give an advice how to go forward with it, interpreting it and seeing what happens, why something happens at a certain stage.
That's really kind of you, Jussi.
No problem. I'm just happy that this is being used. Okay, so this is the major output. Now I think we can. Do you still have time if you look at the trace elements shortly? Maybe 15 minutes.
It's okay for me. Yes, I mean you will probably have to repeat some of these steps at a later point for Carolina and myself certainly, and maybe for others as well. Yeah. But sure, I mean let's get it warmed up. I have another 20 minutes or so, and then I have to attend to something else. But
well, that sounds good.
In touch anyway. So yeah.
Okay,
but,
so
this would be good if major and trace elements. This is a good start, and then I guess. As a next step, Carolina can have a look at what good end members we have and find a good crustal end member and a good mafic end member and play with that a little bit. And then we can run them by you see, and then we start putting them in on some next kind of meeting or so. But sorry, this will give us a feeling for what we actually need to look for, what we need to collect. And that's a good starting point, I think.
Yeah, that's exactly. I think I completely agree with Val here. So that's how I would start. So try to find a good initial magma composition and try to find a good wall rock composition, at least something that you can first start testing with. So yeah, that's the way to start. So you can have something for your input sheet.
Yes, exactly.
Okay, so let's select the output that we produced. That's the first thing we do. So this is actually much more straightforward than the major element tool in a way that, again, well, you proceed downwards here, but the input is, I guess, more self-explanatory here. So first you select the output, and then you can go to select elements which you like to model from the periodic table of elements. So you can click any ones that you like to model. Oxygen is selectable. So if you have oxygen isotopes will run here as well. Of course, oxygen is not a trace element, but it's included here in the same trace element sheet. But it's of course modeled as it should be in the system.
No boron, you see.
Yeah, sorry about that, but there's a way to trick MCS in modeling boron as well.
Make it believe it's something else, yeah.
Yeah, you can make it to be something else. So, for example, I did tungsten isotopic model some time ago, and there's no tungsten selectable. This is related to the. I don't have to go to details why this has to be like that. But I modeled tungsten as osmium. I just made a note in the end that okay, osmium in this table is tungsten for me. So you can use any element, but of course it's more convenient if you are modeling the correct element.
Like lithium maybe instead.
Yeah, for example, because it's all dependent on the input of your whatever you input as your composition, or whatever you input as your partition coefficients. Like that's the one that makes the difference, not exactly what element is.
Yeah.
Okay. Yeah, the element is only the label, I take it, but indeed it's the
exactly.
It's only the quantitative data and your partition coefficients that are specific, and if you can set them, then I mean boron is traveling under a wrong label, but it does exactly what it's supposed to do. So that's my kind of way of looking at this.
Yeah.
That's exactly correct what you said. Yeah. Only difference is the oxygen. So oxygen is modeled differently than the others. So
yes, I can see that because that's 50 to 60% of the system. So.
So I think for this model, I think I have stored, because we don't have to spend several hours to finding partition coefficients. So for this run, I have some stored already. So let's select neodymium, strontium, and oxygen, for example, and let's take, I think zirconium is also available for this set. So here you can set the. Oh, this is so small. I think I have to zoom every window separately. That's a little bit painful, but anyway. So you input the initial concentration here. Of course, you don't need it for oxygen because that is already modeled in the major elements part. And then you can select the isotopic ratio for the element. And then is the input for partition coefficients, which you can find from the literature. They are all 1 as default here.
Okay, so it doesn't come with inbuilt KDs. You need every time to tell it, right?
Yes, but just contact me if you want some sets of them.
Okay, yeah.
Because I have compiled some predefined sets that I'm actually using for many models now.
Yes, once you have done that, you should keep them safe because you don't want to do this each time again.
Exactly, that's right. You can do loading and saving. Okay, this is probably important for Sarah also, like for your question. You can load and save predefined sets. So if you use some set, you spend some time finding good values, you can save them and then you can load them. I actually will show it to you soon. But anyway, the reason that all of these are 1 is that we don't want people to use always the same partition coefficient. So for every situation, it's better that they find their own in a way.
Tell it to Jean Bedard.
Yeah, like the ones I used in the past. They are actually not that bad. Okay, but you can also, these menus are so small. But anyway, you can also set a temperature-dependent partition coefficient. So when the temperature changes, the partition coefficient changes, which is more natural, of course. It doesn't have to be constant here, which I think is a very important thing. If you're modeling a system that fractionates from basalt to rhyolite, you don't want to use the same partition coefficient for the same phase the whole time. So it's better that it changes. Of course, it requires, again, a little bit more input to do that. Then there was a fluid phase present. So there are also fluid partition coefficients, which are very scarcely available. But what I have usually done is that make the element incompatible to fluid, so it doesn't kind of like mess it up. But if you have good values for those, you can use them as well. Fluid is usually a very small part of the whole system, so it doesn't make that much difference usually. But something probably we can return to it when Caroline has run her first models, whether if we have to consider those. Same for wall rock, initial composition, isotopic ratios and partition coefficients, quite a wide range of phases stable in the wall rock. And for recharge, you only need the initial concentration and the isotopic composition, because recharge magmas, they are always mixed with the magma chamber, so we don't need partition coefficients for that. Okay, but here's the one thing that is important. So loading or saving. So you don't have to always input this by hand. You can use predefined sets that we store as these so-called PAR files. I'm sorry that these menus are small, but you can just click if you want to select compositions for wall rock, for magma, partition coefficients, concentration, isotope ratios, whether you want to save or load them. And I think I have there's the default PAR file stored for this run. I'm loading it. They are also Excel lists, so you can easily input your own values in an Excel for these files.
Are there thousands of partition coefficients?
Yeah, because it's kind of like in the same file. Wow. This file, it's stored for all phases that are possible. Mm. But I mean, most of the values are one there as well. So I could save some time by making that list actually smaller. But it usually takes. This is quite slow now. It usually doesn't take this much time to download. So I just have full list of different values there. So now you can see that it has filled these. So strontium content is 226 ppm, 70 ppm of zirconium. And there's the isotopic composition for oxygen. And values here, for olivine, there is a constant partition coefficient because olivine is only stable in the beginning. So we don't have to change that, and anyway, they are very low. I think these are the John Bedard partition coefficients that Sarah mentioned. But for the other ones, then we have temperature dependent partition coefficient. So, whoops, I think I probably should not do that. So basically these values tell at this temperature, the partition coefficient is this, and this other temperature is this, and then it calculates logarithmic correlation between those values. So it models every temperature, it has a new partition coefficient for these values. And then we will just perform the simulation. This will, I think this will take some time now again. So if you have any questions or anything else at this point, we are soon finished with this. I will only show you the final output. Quite a lot of things already at this point, I think.
Millions of questions. No, I actually have one. I saw that Josh Davis, he successfully used this to model shale, basically a simulation from in Camp Sills, and that was very nice. But I was wondering if I mean, shale is rock that I mean, it's full of silicates, whatever. It's very polite. But what about an evaporite? I think both Francis and Valentin might be interested in this question actually, because trying to model something like that, I feel maybe limestone perhaps, but evaporites, yeah. What's your opinion in this? Because
I
think this.
I've been involved in a project with Etna. And in Etna, there's assimilation of limestone in the system, and Melts doesn't like limestone.
I know, yeah.
So and I would think evaporitic compositions would be not very good as well. It just can't, because it's designed for silicate systems.
Really?
So if you have a carbonate system or sulfate system, then the phase equilibria, they are not.
I was just about to ask you about carbonates, how it handles that.
So how we did it in the Etna case is that we mixed some pure limestone with some shale up to the point that it was able to model it. But of course that then loses some detail, and it's not a very good compromise. But that was the only thing that worked.
Mm.
Yeah, and plus this I mean, melts, and in general MCS works on the idea that you're actually melting or partially melting the whole rock.
Exactly.
But usually you don't really melt an evaporite. Maybe there's something going on. But
well, this style of modeling that we did here is partial melt modeling. But you can actually trick MCS to bulk assimilation by putting wall rock as recharged magma.
Oh yeah.
Because that will then, force it into the chamber.
It would be mixing, basically, yeah.
Yes, it's mixing, basically. So you can do that as well. But again, the composition should be something that Melts understands.
Yeah, I had that feeling. But still, I have like, I don't know, 5 cases in which I want to apply this regardless.
Yeah.
But even mixing is not ideal for very volatile, rich wall rocks. So I don't know if putting carbonate as a recharged magma would really faithfully reproduce the process.
But again, like this is one thing that I always mention in these kind of cases, that you kind of like, there's a preliminary idea that this won't work, but it may be fun to test it, and there may be something surprising coming out of it in a way that there's something that works in it and something that does not, that can give you hints to go forward.
I think the isotopes could be very instructive. So, but maybe the major elements might be a bit tricky. Yes.
Jussi, what's the status of your work on Etna? Is that published or?
That was actually a master's thesis in the United States that is not published yet. I don't know if the manuscript is in preparation. It was Mari Takash, who is Wendy Borson's student, or was back then, and she is a PhD student in Oregon now, I think. And last time I saw her, she was preparing a manuscript from that, but
Yeah.
I'm not sure whether that will be out.
Yeah, because it would be interesting to test this in places where we have tons of really good evidence for carbonate assimilation, like at Merapi, see if
Yeah.
we can replicate some natural compositions there. And
That is-
Val and I have bucket loads of data for Merapi, so I think we could test it out there
Yeah.
if you're interested, Val.
Yeah, I could also, you know, see how it, or help in also, you know, probably saying if something, or if you try it first and if something is going wrong, maybe ways to go further. But the carbonate or any other like non-silicate systems have been problematic in the past. I know Melts is just not designed very well for that.
It was never made for that, you know.
No,
Melts was
no.
to actually get crystallization under control, and
Yeah.
this was where they started out in their design, and it was never meant to be an assimilation tool. And this is where, as Sarah put it, this is where the marrying between the energy constrained AFC and the melts comes in. So it's this what the partner brings, not what was there in the original kind of melts component.
That is true.
So,
Yeah.
Okay, so this is now the same input file. So the trace element modeling created 3 additional tabs to this same file. And again, in all the input is again stored here. So the partition coefficients and the initial concentrations and so forth. And there's some parts of the input stored here in the beginning also from the initial output, I mean. So there's the MgO contents and so forth of the magma. And then you can follow the trace element composition here. So strontium concentration in the melt, strontium isotopic composition of the melt. Of course, that doesn't change until assimilation begins. So we have something foreign being mixed in the system. Zirconium, neodymium isotopic composition. And then you can also, if you're interested, to follow every trace element in every phase. So how much zirconium there is in olivine, how much zirconium there is in feldspar. So again, quite overwhelming amount of output. Bulk solid, so what is the bulk amount of these elements in the cumulate pile is also stored. And the partition coefficients and so forth. And the oxygen isotopic composition is here as the latest input. For oxygen isotopes, we are not considering the fractionation during fractional crystallization because the amount of that is usually so small that it's only following the mixing part of the that system. One final thing I want to show. I think we don't have to spend more time with this because you can read these outputs whenever you like. One final thing I want to show because this was so cool. Everything you've seen so far is just Excel tables. Sometimes can be quite tedious. But I had a postdoc for 4 months in this project. Brilliant person, and he created a visualization tool in those 4 months for MCS, so you can actually see what happens in a magma chamber. So
Cool.
I will show that soon for the same run that we've been looking at all the time. So there is melt and wall rock. You can see there's quite a high amount of the wall rock. Like mentioned, that this is very like extreme case in that respect. And you can just follow here. You can make this run as an animation, or then just move this block here yourself and see what happens. Like there's crystallization taking place. First is olivine, clinopyroxene, and feldspar starting to crystallize here. So kind of like creating this kind of layered intrusion, although they are not really how this forms. And now the wall rock started melting, so you can read the relative amounts of the phases in the wall rock when it's being molten. And there is recharge event. The mass of the magma chamber increases. Crystallization continues after that. The amount of wall rock getting smaller because being melted. There was another recharge event there. And this is basically how you can just follow it. And maybe we've also used this in publications already. So it's not just this is an image that you can show that, okay, this is what happens in the simulation quite fast, and showing quite a lot of information in one figure. So in the end, there was still quite a lot of melt left, and there's the small fluid bubble, that was separated in the end of the run.
See, that's the problem with carbonated simulation. That fluid bubble would be huge, or times 100. Or...
Yeah. I mean that, but CO2 is part of the CO2 is part of the melts algorithm. So it should also, if there's too much CO2 in the melt, it should spit out a huge bubble of CO2 fluid.
Yes, it's going to be bigger than the entire diagram.
Yeah. But anyway, yeah, this is what I want to show.
Nice, this visualization. I've seen it in one of the things you sent, and I think it's lovely. So it's really useful. Because yes, the Excel spreadsheets are, they are functional, I think, but of course they're not very visual. While this is a big step towards kind of getting a quick overview, and this is very nice.
Yeah.